talk about from vortices to Vermas, and according with my great tradition of mutilating people's titles, I forget the rest.
Well, thank you. So yeah, it's really awesome to be back here, and I just want to thank Jake and his colleagues for the opportunity and the Newton Institute. So my background is in physics, and I want to tell you today about some constructions in three-dimensional gauge theory that may have interesting implications for geometric representation theory, and hopefully great actions on categories and the sorts of things one wants in categorification. So on my end, this is past and ongoing work with Davide Gaiotto, Matt Bullimore, who's currently a postdoc at Oxford and moving to Durham, and Justin Hilbert, who was a student of Nick Proudfoot's and is now a postdoc at Penn. It's also closely related to recent mathematical work of Braverman, Finkelberg, and Nakajima, and recently work by Camden and Webster that I'll also discuss. So my initial motivation for starting this whole investigation a few years ago was to indeed make sense physically of categorical braid actions that many of you have defined. There's an entire zoo of these things. So they're braid actions on coherent sheaves, or Kaya category, or modules for some non-commutative algebra, on lots of different spaces, things like flag, or Slodovy slices, or slices in affine Gaussianians, or Nakajima quiver varieties. And so I wanted to embed some more of this into physics, and in particular understand why they all seem to be giving the same result. Why you could basically choose any ingredient over here and any ingredient over here and get the same braid action. At least that seemed to be the status as far as I understand it. So I have a little bit to say about that. Also, a great inspiration for what we did came from work of Braden, Licata, Proudfoot, and Webster on symplectic duality. In particular, they choose D modules over there, and then they relate various pairs of spaces on the right. So there's some so symplectic duality, as they defined it, is a statement about an equivalence of derived categories of modules associated to various pairs of spaces. Okay, that's sort of mathematical motivation. In physics, gauge theories and string theory have been used for a long time to construct topological invariants of manifolds, knots, all sorts of things. And almost as long, physics has been used to propose categorifications of these invariants. So we're going to hear a whole lot about that next week. These 3D theories that I'm talking about are sort of a small part of a big set of interconnected physical theories that are ultimately trying to describe the same thing. So this is providing one particular perspective on a big problem. Should also say that, so I'm not actually going to say very much about braid actions in this talk. This is the next thing we are trying to work on. I will talk about categories of modules. The braid actions that arise here, at least on one side of symplectic duality, are closely related to work that Bukov and Whitman did in terms of local Langland's correspondence. So they defined some braid actions and quantum field theories that are very similar to what I'm going to tell you about. So let me tell you what I'm going to tell you. So the plan is to just since this is mainly a new audience and a very diverse audience, the plan is to start by saying a few basic things about three-dimensional supersymmetric gauge theories. And to introduce some physical concepts, a moduli space of vacua and local operators, particular algebras of local operators, which are going to provide holomorphic functions on these spaces, and then how to quantize them. So if you're coming from a math background, I think in part this section of the talk is just going to be forming a bit of a dictionary, inserting physics words in some well-known mathematical constructions. In part. Also, if you're coming from a two-dimensional mirror symmetry background, these should all be familiar, sorts of ideas should be familiar from there. And I want to include, one more object that's familiar in 2D mirror symmetry, namely boundary conditions. And tell you a bit about how boundary conditions look in these 3D supersymmetric gauge theories, and what one gets from them. So to take a shortcut to the end, so boundary conditions are going to end up giving us modules for algebras of local operators. If we quantize these algebras, they're going to be something like the modules. And these 3D theories are going to have not just one, but two different algebras of local operators corresponding to a pair of spaces over here. And by taking a single boundary condition and producing simultaneously modules for both of these algebras of local operators, we'll start to get at the symplectic duality statement. And then there's, right, so the description of boundary conditions that comes up in physics is not exactly what one would use in mathematics, and that's kind of nice and interesting. It gives a new perspective on constructions of modules for these algebras. And so one that I'll hopefully get to at the end is how to build Verma modules for one of these algebras, and we'll see that Verma modules come from, Verma modules on one of the spaces in symplectic duality come from looking at quasi-maps into the other space. That generalizes some work by Braverman, Finkelberg, and Nakajima on what they call a finite version of the AGT correspondence. That's probably all I will actually have time to say. Maybe say a bit about how interfaces and braiding and so on should come about, but probably not. Okay, and please interrupt at any time. So let me say things about 3D gauge theories. So 3D n=4 gauge theory. The n=4 is just saying how much supersymmetry we have. I'll even say more about that in a second. So one of these theories is determined by just a few choices. So there are some discrete choices which at zeroth order are the important ones. So one has to choose a compact group, G, this is the gauge group. And a quaternionic representation R of G, which is sometimes called the matter representation. And I will assume throughout this talk that this representation is the sum of a unitary representation and its dual. Right, so you can think of this as T star. Let's see for some. Then there are continuous choices. Which are extremely interesting and play very important roles in all of the following constructions, but I am not sure I'm going to have time to actually say very much about their important roles, so I'll just mention them briefly. So these are so-called parameters in the physical theory, things one can tune to get families of whatever. So they're related to, the important ones are related to other groups in the game. So we'll define a group GH to be the maximal thing that acts symplectically or quaternionically on R, that's independent of G. So what I actually mean is the normalizer in USP R of G, mod G. But it's sort of the residual part of the full, so here there's a USPN acting, I mean the residual part of this after G is taken into account. So then there are masses which are infinitesimal M, they're infinitesimal co-characters of GH. So when we think of them as living in the carton of TH, and everything in this game is going to be hyperkähler, so it's in fact three copies of the carton of TH. And there's a second set of parameters, 5 parameters, which live in 3 copies. They're infinitesimal characters of G. I can also think of those as co-characters of the Pontryagin dual group of G. And so there's secretly a GC sitting around. It's sort of going to be the mirror to GH. So I've got infinitesimal co-characters of GC.
What does FI stand for?
It's historical and supersymmetric. It's their 2 initials, Valle Iliopoulos. It's a particular term in the supersymmetric Lagrangian of gauge theories. Yes, so we've got these. We actually have one more parameter, which is a normalization of the killing form on the Lie algebra of G, which really plays no role in the ensuing discussion. And that's it. Okay, so given G and R, and maybe these, there are lots of things one can compute. In particular, as a physicist, one would write down a quantum field theory. That means writing down fields. So we can define fields. So these are sections of particular bundles on R3, and it's R3 because I've said it's a 3-dimensional quantum field theory, and since it's a gauge theory, this includes a principal G bundle. And an action that's a function from the space of sections to R. And great, so the bundles I'm using depend on G and R. The action additionally depends on M and T. And then we've got ourselves a path integral. That's an integral over field space with a measure e to the minus s. And just to say some more really basic physical things. So one talks about working classically or quantum mechanically. So classical quantities, so working classically, means just working on the critical locus of S and working quantum mechanically means working with expectation values inside the path integral. So there are various relations that hold classically, that just means they hold on the critical locus of S. And there are quantum relations, which are things that hold inside expectation values. So this means working. I realize this is incredibly sketchy. So they're relations that hold here. So one hears the word quantum corrections very often. That what quantum correction means is that it's something that holds an expectation value. Okay, so one more ingredient. So there's supersymmetry around, and you may wonder what that has to do with anything. So supersymmetry means that there's a graded algebra that acts on fields. It acts on functions of the fields. Acts on everything in sight, such that well, several things, such that S is preserved. That's the notion of this being a symmetry of the quantum field theory. But it's a very special graded algebra. So n equals 4 for, again, historical reasons, means there are 8 odd generators. And these are always written as Q with some indices, and the odd generators have to contain translations in their anticommutators. So translation generators in R3. So there's an algebra of translations acting on fields because there's sections and bundles on R3. Okay. That's supersymmetry in 2 minutes.
To clarify, when you say graded algebra, you mean Z2 graded Lie algebra?
I do.
Super algebra.
I do.
Yeah. Not some.
No.
It's lots of graded
Indeed.
algebras.
Yeah. That's exactly what I mean. So, okay, why do we care? So a huge benefit of having supersymmetry around is that there often exist, and there certainly exist here, many nilpotent elements in A. Nilpotent odd generators. And very nice things happen when working in Q cohomology for one of these nilpotent Qs. And this is the principle behind localization of path integrals, or about anything in a topological quantum field theory that's not Chern-Simons. One is always working in some sort of Q cohomology, and that allows precise computations of various quantities. Okay, so we had a specific supersymmetric quantum field theory. It was determined by G and R. And we're interested in 3 basic objects: moduli spaces, operators, and boundary conditions. They are all sitting inside some Q cohomology, and in fact inside several. Let me tell you what they look like. So first basic object is this moduli space. What is it? Well, classically, so I want the moduli, write all the words down. So it's the moduli space of supersymmetric vacua. In the theory, classically this means the intersection of the critical locus of the action and the fixed point set of A. Acting on the fields. To be in the fixed locus of A means in particular that translations act trivially. So we're talking about constant sections of these bundles that sit on the critical locus of the action. In our theory of interest, this moduli space is a finite dimensional hyperkähler manifold. Manifold is too much, maybe. Yeah, it's a finite dimensional hyperkähler space with certain singularities. And let me move back up to the other one. This. Yes. So notably, this space, in a rough description that I'll improve in a second, it consists of two components, so-called Higgs and Coulomb branches, sorry, so I told you classically what it was supposed to mean. I haven't told you quantumly what it was supposed to mean, but the full quantum thing is a finite dimensional hyperkähler manifold, and that's what I'm defining. So there's a component called the Higgs branch, which is the hyperkähler quotient of R on G. So that means set the triple of hyperkähler moment maps to 0 and divide by G, or if you're an algebraic geometer, you set the complex moment map to 0 and divide by an algebraic group. The other component, the Coulomb branch is a little trickier to describe. It's a vibration.
Can I just ask, we often use parameters when you make hyperkähler quotients.
Indeed. So those are, yeah. So I was going to say it later, I can say it now. So the T's are characters of the group, so they fit here. So that the T's resolve this space, the M's are going to resolve the other space. It's less obvious to see why. But yes, the parameters are around. There are no parameters that I haven't told you about. So one of these is a simple hyperkähler quotient. The other one is a vibration that can be viewed, kind of depending on whether you're a hyperkähler geometer or an algebraic geometer, in two different ways. So either it's a dual torus vibration over 3 copies of the Cartan-Leibniz, or it's a complex torus vibration over the complexified Cartan Leibniz. With a singularity structure, singularities of the fibers, determined by the representation. So here it looks sort of like only the group is entering in. This is the torus of our gauge group. But in fact, the actual structure of this vibration is determined by R. So nevertheless, the quaternionic dimension of the space is the rank of the group. So in this description, the Higgs branch, if these moment maps are actually zero, is a hyperkähler cone with some cone point, and the Coulomb branch intersects at the cone point. So the Coulomb branch also has a most singular point sitting at 0 in the base, where in fact all the fibers generate, and that's singular points are meeting. And now I can improve the rough description. So what actually happens is that the Higgs branch is stratified. The strata are labeled by subgroups of G that stabilize them. In the hyperkähler quotient. And out of each stratum labeled by some subgroup, you get a Coulomb branch corresponding to that subgroup. So there's a stratum at 0, which is stabilized by everything. You get a big Coulomb branch sticking out of it. But there might be other strata. And these are submanifolds of the big Coulomb branch. There's this sort of intricate structure where both Higgs and Coulomb are stratified, and they connect in some interesting way. This might also be familiar from, if they're thinking about derived stacks or derived singularities or things like that. What it seems like is that this is a picture of derived hyperkähler singularities, where the derived structure is encapsulated in these Coulomb branches. There are lots of hints that that's true. I don't think it has been made fully precise. I'm not actually sure about the mathematical work that studies derived hyperkähler singularities, but it might be wrong. Okay. So, yes,
Would you call these mixed branches, or that's
yes, you would call these mixed branches, indeed, where there's a stratum of the Higgs branch with some stratum of the Coulomb branch sitting everywhere on top of it. That's right. So there were masses on F5 parameters around. So the T's resolve or deform the Higgs branch while putting a potential on the Coulomb branch, and the M's do the opposite thing. The potential comes from, so the M's and the T's correspond to symmetry groups. They're infinitesimal co-characters of symmetry groups. Of T is a symmetry group on the Coulomb branch, M has to do with a symmetry group on the Higgs branch, and these potentials come from moment maps for the groups I talked about briefly earlier. They're symmetries of MH. Now, some words. So, a systematic construction of Coulomb branches wasn't actually known until quite recently. we proposed a bottom-up construction of the algebra of functions, talking about generators and relations. Braverman, Finkelberg, and Nakajima gave a really beautiful top-down construction that was mathematically precise and for the first time allowed mathematicians to start rigorously making statements about Coulomb branches and 3D gauge theories. I want to talk about that in 10 minutes. Despite the fact that a systematic construction of Coulomb branches definition has not come until recently, it's been known for a long time what several pairs of Higgs and Coulomb branches should be. And so I'll just give you 2 examples. If the group is E1 and the representation is T star and C to the n, where U1 acts with weight 1 on all copies of C, the Higgs branch is the minimal nilpotent orbit in SLN. It's resolved to T star Pn minus 1. The Coulomb branch is C2 mod Zn. Hopefully a pair of spaces that has come up often. Another example, if G is a quiver gauge group, and R is the quiver representation, for a Nakajima quiver variety, then the Higgs branch is the Nakajima quiver variety. And what is the Coulomb branch? Well, in general, it's a complicated thing. If this is an ADE type quiver, then the Coulomb branch is a moduli space of singular ADE monopoles. Trying to think if some part of that statement was actually developed here many years ago. Mathematically, this corresponds to a slice in an affine Grassmannian for ADE. So it's a slice ADE and Grassmannian. So again, these are 2 very fundamental spaces that show up.
What are the potentials in these cases? Like, is it easy to tell, or is it?
I mean, it's always the moment maps.
I mean, for example, for T star Pn, what's the potential that you get if you turn on T?
Yeah, exactly. So T star Pn has a PSUN hyperkähler isometry. You take its torus, or take some U1, and so what the P's or the M's, whichever the right one is, what it's doing is telling you how to choose a U1 subgroup of the hyperkähler isometry group, and then we're turning on a moment map for that U1. Okay. The way, right? The way any sensible description of the Coulomb branch comes about is by saying what the algebra of functions is on it in some complex structure. Yes, so obviously time is passing quickly. Let me try to say this succinctly. So the algebra of functions on the moduli space comes physically from looking at local operators in the theory. So to summarize that. So for either MC or MH, for each one, they're independent statements for each one. There's a set of local operators in the QFT. Whose expectation values are holomorphic functions in the complex structure of your choice. So for either one of these in a fixed complex structure, gets holomorphic functions on the Coulomb branch or on the Higgs branch. It's the basic statement. So what I mean by a local operator is a function of the fields, in the simplest case. It's a function of the fields supported at a point. So I don't have time to say very much about this. I'm going to do this by picture. So some point X in R3. The fields are sections of bundles over R3. Local operator is some function, the values of those sections at a point. It can be inserted into the path integral. So one can take such an operator, compute its expectation value. Actually making sense of this on R3 requires a choice. It requires precisely a choice of vacuum at infinity. This depends on a point P in the moduli space of vacua. So there's a pairing between operators in the field theory and vacua. You always get some sort of function on the moduli space for any operator. And the point is that there's some special ones that give you holomorphic functions. The statement is important because, well, a lot has been done mathematically with operator algebras. Obviously, there's a workshop about it. Anyway, so this is relating holomorphic functions to an operator algebra in a three-dimensional theory. These are operators that sit in a very special Q cohomology for some supercharge, and they behave nicely. Expectation values of operators inserted at two different points don't actually depend on the position of the insertion points. Working in Q cohomology trivializes translations and deformations. That means there's a collision operation. Bring the points together and take a product of operators. That's the product in the rings of holomorphic functions. So collision operators corresponds to a product in these rings. There's actually a lot more structure which mathematically shows up just in the abstract structure of TQFTs. So in 3 dimensions, an operator algebra has to be in B3 algebra. That means it comes with a Poisson bracket. The Poisson bracket here is the one coming from the holomorphic symplectic form on the manifolds. So So I should say these operators don't just give rings of functions, but they give rings of functions as Poisson algebras. And there's a deformation of the quantum field theory that quantizes these Poisson algebras. And quantize the operator algebras. So a priori, this product of operators in a three-dimensional theory is commutative. These are points in some 3D space, and nothing depends on the position of the points. So you can just move them around each other any way you want. To make the product non-commutative, choose an axis in R3. And work equivariantly with respect to rotations. Around the axis. Now that has several names. So in physics, this thing is usually called turning on an omega background. If we're working in cohomology of some supercharge, what's literally happening is that we're deforming our differential so that it no longer squares to 0, but it squares to some multiple of rotation. And then local operators are forced to live on a line, and they no longer need to commute with each other. Mathematically, there's a canonical deformation of E3 algebras to E1 algebras that takes a commutative thing with a Poisson bracket and spits out a non-commutative thing where the Poisson bracket has been quantized. Okay. So, yes.
Sorry to keep interrupting.
Sure, sorry.
So your R3 is not really R21, it really is R3.
It really is R3. It's a bit. It's a Euclidean.
You've done something.
I have. Okay. So, boundary conditions. Last ingredient. So, right, so I built this picture of operators. Living at points, of the algebra of functions on the moduli space, actually corresponding to points in three-dimensional space or on a line, with collision being the actual product in that algebra. If we want modules, well, we should think about a half space and have, say, some Higgs branch algebra in the upper half space. These can collide with each other in a commutative way, but they also collide with the boundary of the half space, and there's some other boundary B. There is some other algebra of operators on the boundary. We can just think of it as a vector space and get an action by collision of stuff in the bulk with operators on the boundary. We get an action. We get an action like that. Now, physically, what I mean by a boundary condition, well, classically, it's literally a boundary condition for equations of motion. There's some differential equations. I need to choose appropriate boundary values to get nice solutions. And in a quantum field theory, maybe a better way to say it is that this is just a two-dimensional theory. And it's precisely the sort of two-dimensional theory that shows up in A models and B models we heard about in the previous talk. It's a two-dimensional theory that's sitting at the boundary of space and interacting with the 3D theory. It has some algebra of operators. It's what Hochschild cohomology of some category. And that's what this is acting on. There is a similar picture that involves an axis. So if we quantize, things look even better. So at the boundary, everything lives at a point. That's a vector space. So there is some vector space M. And the picture says that the quantized algebra of functions on, say, the Higgs branch or the Coulomb branch acts on this M. Okay.
What is M in terms of the? Is there a way to get to M from the OPSP?
Yes. As a vector space, it's exactly the same.
So, but there is no product or anything.
There's no product. Exactly. Yes. Okay. So, concretely, that's just a picture. If you want to compute anything, so one, there's a way to classify a very large subset of boundary conditions. Let's say, well, it's classifying boundary conditions is very similar to classifying two-dimensional 2-2 theories. Landau-Ginzburg models, the nice ones, or gauge linear sigma models. So gauge linear sigma models with the potential basically give you boundary conditions. Roughly. Boundary conditions, or some large set of them, are classified by two choices that relate to G and R. By a choice of subgroup of the bulk gauge group. It's going to be the one that still acts at the boundary, and G prime invariant Lagrangian splitting of our big representation. And so if we rewrite it as R plus R dual, this is always a Lagrangian splitting, but there are in general many of them. So those are the two basic choices, and then there's all sorts of stuff that you can add on top of that that have to do with gauge linear sigma models on the boundary. Which I'm sorry, I don't have more time to talk about. So then, given some data for a boundary condition, we can compute and actually find modules. And the idea was that any boundary condition simultaneously gives a module for the Coulomb algebra and a module for the Higgs algebra. Let me just give you a short example of that. So if G is U1 and R is, well, anything. So I had a specific representation that gave me, had specific weights that gave me T star Pn before, but you can use anything, then the Higgs and Coulomb branches are both hypertoric varieties. If I choose boundary conditions where my subgroup is the entire group, G, and consider lots of different Lagrangian splittings of the representation R, then I end up with simple modules for the quantized algebra of functions on the Higgs branch. So these simple modules, their support is just just comes from pulling a Lagrangian through hypercarrier reduction. You get some smooth component of the Higgs branch out of this. On the other hand, for the Coulomb branch algebra, what we find are Whittaker modules. For the Coulomb branch, which is not right. So it's not the usual way that symplectic duality statements go. There is a further deformation of these that turns into tilting or projective highest weight modules.
What are the two algebras in question in this case?
Yeah. So in general, they're just called hypertoric enveloping algebras. But if I want, say, if the Higgs branch is T star N, this one, then the Higgs branch algebra is just the enveloping algebra of SLN. The Coulomb branch algebra is called the symplectic reflection algebra. It has easy generators and relations. But yeah. So on this side, well, it's a big quotient of the enveloping algebra of SLN. And so we literally get SLN representations. Highest irreducible highest weight SLN representations. We do this right here. And on the other side, complicated things. Describing them as Whittaker modules is actually really nice. It's much nicer than talking about successive extensions that give tilting or projective modules. Right, let me try to maybe wrap up conceptually and say one more precise thing. So this correspondence of modules is sort of a basic kernel of the symplectic duality phenomenon. So one can take lots of different boundary conditions, stick them to this machinery, and get pairs of modules that should correspond under symplectic duality. The way symplectic duality is actually phrased in the powerful statement is an equivalence of categories. And that is somewhat harder to justify, even physically. And we lay out at least an outline for why the equivalence of categories should work in a paper. But I think there's actually a great deal more to investigate there. Great. Let me I want to say one more thing. So, and that's related to the Vermas and the vortices. So how do you actually do these computations? You can compute spaces of local operators on the boundary of some 3D theory. Though another thing that it is possible to do with the boundary condition is to wrap it around the boundary of a cylinder. In other words, consider the theory on a disk times time. We can work equivariantly here with respect to rotations about some axis, so that operators all lie on this axis. And claims that in this theory, there's a natural notion of a Hilbert space. So this is the Euclidean time, that's fine. There's still a Hilbert space associated to the disk. So there's a Hilbert space of the disk that depends on this boundary condition, B, in a crucial way. And the claim is that this, again, is a representation, the same one that appeared above. This is a representation of the algebra of operators, be it the Higgs or the Coulomb one. Right, Coulomb, because that's relevant for what I'm about to say. And this can be computed in a precise way. This Hilbert space ends up being the cohomology of a moduli space of solutions to some differential equations. And the action on it comes from correspondences. It is some convolution action. And if we play this game with the right boundary condition at boundary of the disk, we recover the BFN construction, or Braverman, Finkelberg, Nakajima proposal for what the Coulomb branch algebra actually is. This picture doesn't give you immediately the algebra of local operators. What it gives you is the representation of this algebra in a particular Hilbert space, but many of those representations are faithful. So you can recover the algebra from the representation. And if you play this game with a slightly different set of boundary conditions, you end up, so the Braverman, Finkelberg, Nakajima picture has to do with Whittaker modules. There's a corresponding picture that has to do with Verma modules. And just write it down. Finds that Verma modules come from taking the cohomology of spaces of quasi-maps into the Higgs branch. So let me just talk about the BFN boundary conditions. So here we're going to take the boundary condition. Well, it was defined by these two basic pieces of data. So we're going to take G prime equals G for any theory, and choose some Lagrangian splitting. And the thing is, there are many choices. There's no canonical choice, and I think it's actually still difficult to say mathematically why two choices should be equivalent. Anyway, there's some choice. Say, at the beginning of the day, we wrote unitary representation plus dual. Let's take that splitting. Okay, then the idea is to consider a moduli space of supersymmetric field configurations on a disk, which ends up being a triple, a holomorphic GC bundle on a disk, and a section, holomorphic section of a curly R bundle, of an associated curly R bundle, where X and Y are in non-curly R and R dual, such that the complex moment map on X and Y vanishes, and we have to impose a particular boundary condition constraint. So the way the boundary condition comes in, if X is an R and Y is an R dual, we're just going to set Y, the boundary of the disk, to be 0. That's the boundary condition. Well, right, so before I said that this holds for any boundary condition, with this in place, well, if you have a holomorphic section that's 0 at infinity, it's 0 everywhere. So Y is just 0. So in fact, the space, depending on that boundary condition, is just pairs Unix, such that blah, blah, blah. And I can completely, well, such that X is a holomorphic section of R. And I can completely remove the complex moment map constraint. And its cohomology is the Hilbert space. So HB is just Durham cohomology. And then if we want, we can work equivariantly with respect to root rotations. And turns out this is, the entire space is contractible. This is equivariant cohomology. Sorry, there's a divide by complex gauge transformations, moduli space. So this just being, it's just cohomology of point mod GC, which is polynomials in the complexified Cartan and our parameters, our root rotation parameter epsilon, G invariant. This is a thing that the Coulomb branch algebra acts naturally on in a Whittaker-like representation. So the Coulomb branch algebra comes from looking at local operators and surrounding them with two disks. So here's my disk times time, a little raviolo. It's two disks surrounding a local operator. The union of the puncture disk with D. So there's some similar space of bundles. It's exactly the same words. It's bundles on two disks identified away from the origin. dxy and then d prime x prime y prime, obeying exactly the same conditions identified away from the origin. And the cohomology with this is the BFN proposal for the Coulomb branch algebra. And it acts naturally on that. Functions on the algebra. As some sort of Whittaker module. This is infinite dimensional and a little bit nasty, and so the right thing ends up being more homology rather than cohomology. That's the essence of the statement. So, right, so, sorry, I'm going to say in words the last part, so title of the talk. So if you do the same thing, but work with a resolved Higgs branch to turn on T's, so that you have something like P star of Pn rather than a nilpotent orbit. And consider some U1 action on this resolved Higgs branch that has isolated fixed points. So we can define a boundary condition that just says extend the disk to be infinite, make it a copy of C, and force the fields to sit at one of these fixed points on the Higgs branch at infinity. Then just running through the exact same construction, makes this thing roughly speaking, it's homomorphic maps from P1 into the Higgs branch, where infinity goes to some fixed point. Based homomorphic maps, but that's not quite right. It's maps into the stack, or people call them quasi-maps. And then you run the same statement over here, you have to have some boundary condition. And we get an action of the Coulomb branch algebra on the cohomology of spaces of homomorphic maps. And that ends up being a natural way to construct Verma modules for the Coulomb branch algebra. Okay, so, sorry, that's roughly how things go. Please ask me later if you'd like more details. There's one more step in this game, namely including something about braiding or Nakajima-like Hecke correspondences, having some sort of algebra actions on these theories. And that's going to come by, instead of boundary conditions, having interfaces. So say we have a theory labeled by some quiver variety with certain ranks, and some other quiver variety with other ranks that are connected by some interface. And so this running the same sort of game should give a way to understand these actions simultaneously, both on the Higgs and Coulomb branches. A lot of that is already known in math. I am hoping that the physics construction will lead to something slightly different and interesting. This quasi-map thing was not known in math, except in some very isolated examples. Thanks.
Questions?
In the case where the Higgs branch is T-star flag, like type A flag, so then there's this Finkelberg-Kuznetsov construction of Verma modules on these kind of quasi-map spaces. I mean, I think this is very old, like
Yes.
late 90s or something.
Indeed.
Is this
Yes,
the same?
it is the same.
So then there's also a version that some construction which does something similar, but not for based maps. And then they get something which I think they conjecture is a tilting module for SLN. Like you look at moduli space of holomorphic maps from P1 to just to the flag variety. But
So I didn't know about that.
Yeah,
that's interesting. I would have.
and I think it's, I don't know if it's known now, but when they wrote the paper, it says we conjecture this is a tilting module.
Okay.
So I was curious if there's some boundary conditions you can write down where you.
Well, it's right. So I only know one way to get tilting modules, and it would be neat to see this. So I only know how to get them from taking nearby cycles of a Whittaker module, where the so in the Whittaker module, the raising operators act as some constant. Sorry, there's a parameter in Whittaker modules. You want to set that parameter to 0 to turn them into highest weight modules. So the thing that would be the highest weight vector is not highest weight. It's an eigenvector for n for the raising operators, and you want to set the eigenvalue to 0. There's some nearby cycles limit there that tells you how to actually do that, and that. As far as I know, it gives all tilting and projected modules you want. You generalize the notion of Whittaker modules a little bit to get all of them, but you do get all of them. And so in fact, this action has precisely one of these parameters. The Coulomb branch algebra is acting as some sort of difference operators here with a parameter, and you set that parameter to 0, and that's how I would get tiltings. But it would be really cool to see a different.
Like, what's the simplest example that I should think about of, a categorical break group action and what the,
Yeah.
what these boundary conditions are for it. And
So there are more precise computations that need to be done, but you have the Nakajima quiver variety. Just take the Grassmann, T-star Grassmann. So here our group is compact cases UN, and there's a framing node. Sorry, does that make sense?
no, I don't know what this picture is.
Okay, so so
I mean, say I wanted to get like the sort of Kavanagh-Thomas break group action or something.
let me try to say it a different way. So so I would construct these in the gauge theory by introducing some two-dimensional representation of the group on one side and the group on the other side. Well, the group is the same if we're braiding, if we're not doing Hackett correspondences. And so it's some representation of G times G that's coupled with a superpotential to the matter fields on either side. That means this is an object in the category of matrix factorizations for two copies of the theory. I think this is a sort of thing that, at least in certain cases, has been studied. Yeah.
Okay.
The precise, so if you think about this as coming from flops, then there's the field content, the representation on the two-dimensional interface is going to have to do with the cycles that it's labeled by data of the cycles that are shrinking. Yeah. So again, I think various effective descriptions of these things have been written down. The goal is to sort of systematize it all in this language.
Okay, strategically, it's important that you quantize all these algebras at the default of the CF. So
It is. It's more interesting. I mean,
you wouldn't end up with, if you just think about the computative algebras of functions on these things, you don't see as much as there.
indeed. And from the point of view of the quantum algebras, these are going to be bimodules. This picture is just a way of saying bimodules. And so it's an action by tensoring with bimodules.
Any more questions? All right, well, let's thank Tudor again.